Mr. Chairman, dear ladies and gentlemen, it's my honor to be here in front of you. Grazie. My Italian skills are fortunately much better than my colleague from Finland, Mr. Pekka Utala. However, since everything is relative, I'm limited up to 4 parole. We in Vaisala have been developing something very much new. It's a new, completely new technology product which kind of comprises distrometer, visibility meter and present weather all in the same. So this new, I would say beautiful opto-electromechanical setup, it is all about nueva tecnologia innovativa. Grazie alla sensibilità superiore, we are able to actually reach the level of the size of precipitation particles which are so small that they are not even coming down in the atmosphere. So small hydrometeors that they actually float in the air, 0.1 millimeters in diameter, which means that we can select that when we start reporting precipitation. So why we are actually doing that is that over the years when we are following what are the needs in the best and the biggest and most significant meteorological agencies and organizations in the world, when they indicate that which are the gaps and shortages in precipitation, present weather and visibility measurements, they always delineate the most important issue is sensitivity for light drizzle and precipitation events. We have accumulated knowledge since decades back, and we have the luxury of having scientists in row, and we invest a lot in R&D and development. So we decided a few years back to run some research studies and really find out how could we fill this gap. How could we achieve the superior sensitivity to detect every precipitation event, particle by particle, not missing a single event. And now it's my honor to present you that we have actually achieved that level. The product is a new platform, it's Vaisala forward scatter sensor FT70. So it is the 7th generation of Vaisala visibility and present weather sensors. So this Nuova Tecnologia Innovativa, it's a combination of two conventional technologies, forward scatter sensor technology and optical distrometer. So what we've actually achieved is that we managed to combine the two, which means that the forward scatter sensor now has a light sheet instead of transmitting light cone. So how the sensor works, it actually transmits near infrared light and then measures the scattering from the transmitted light colliding with hydrometeors, airborne particles, and scattering light to different angles. So with the new technology we actually have managed to select and pick and maintain the benefits, the pros of these two conventional technologies, forward scatter sensor and a distrometer, while getting rid of their most significant cons. So here we combine visibility reporting, present weather reporting, precipitation intensity and accumulation, precipitation identification, as well as we actually provide a full particle size distribution out of the sensor. So the beauty of the technology actually resides in 3 independent things. So the width of the sensor is something like 80 centimeters, so it's like compact, easy to install sensor, which has a transmitter, number 1 there, and out of there we got a near infrared, very, very thin light sheet with very controlled dimensions. So then in the receiver side resides another thing. So basically the light sheet is transmitted in a certain angle downwards, and then the receiver, which is at the angle of 42, looks at a plane, or actually a very thin sample volume in the light chip. And what is new here is that we are sampling the transmitted light at huge sampling rate. So it's 5 million samples a second, which then sets very high requirements to the processor board. So we need to be able to take 5 million samples a second and then particle by particle scan the scattering properties analysis. So this is the new technology, threefold, and this technology, thin light sheet, 5 million samples, and this mentioned 42 degrees optimal scattering angle. It casts the foundation for the future and for everything what we are doing in it. So we are almost there. We are almost able to deliver within a few months this from full scale from production. The internal parameters built on this hardware, optoelectromechanical setup, are fall speed, particle diameter, and then particle scatter properties analysis. So basically we get so many hits from the transmitted light to single particle, the precipitation particle, that we can see, we can actually take a fingerprint out of the particle and then assess with an algorithm that what is the form, what is the state, is it liquid, is it frozen, is it ice pellet, is it hail, is it result, whatever the particle is. So we've achieved here huge improvement in precipitation type assessment, as well as we provide, like optical distrometers, a full droplet size distribution. So we report droplet size beginning from 0.1 millimeter in 40 different bins, 40 bins. Precipitation intensity is one thing, and I have an example on that one, and that relates as well to precipitation accumulation. We report obscuration type, which means if the prevailing condition is foggy, misty, or if there is haze in the air. We also noticed that we managed to achieve an excellent signal to noise ratio, and that enables us to report the visibility, the meteorological optical range over a huge range from 1 meter all the way up to 100 kilometers. And then we have a 5-second measurement cycle. So basically the sensor can report what has happened in the atmosphere over the past 5 seconds, and then if a customer wants a longer average, that's also available. This is a busy slide, but I highlight a few things. We have added snow grains, we have added ice crystals reporting, as well as snow pellets and hail. So for example, hail is an indication of a very severe conditions developing, for example, at an airport. Also, we implemented Ethernet port and IP connectivity on the sensor head. It is an RVR, runway visual range compliant sensor. It has, as mentioned, this, I would say, big improvement across the board when it comes to identifying different precipitation types, such as listed here, the 11. So condizioni very severe. For example, let's take an event where there is a freezing condition, but the particle size is very, very small. It's been very difficult to detect automatically this kind of conditions and precipitation events with some sensors. So for example, conventional distrometers at best, their limit is around, when we are talking about diameter, 0.2 millimeters. And conventional forward scatter sensors, we are talking about half a centimeter diameter before we can, half a millimeter diameter before we can actually have a detection that something's in the air. With the new sensor platform, the model FD71P, the detection sensitivity goes down all the way to 0.1 millimeters. So we've noticed that we are taking actually a big leap towards fully automatic method. We don't miss an event. I have an example event of the performance. This is actually from Helsinki test field. This is a last November case. It persisted for 3 hours, began 2 a.m. in the morning, and it was mostly slight to moderate drizzle, but the particle size was very small. So this was very difficult to detect, and we have a reference set up in the test field, so we could actually replay the event and check how it works, and then adjust the algorithm of the sensor. So we have a wide variety of different sensors in Helsinki test field at Vaisala. Equipment here is an old Vaisala PWD-22 sensor, and then the new FD71P, and of course one of the references a weighing rain gauge, so the collecting weighing rain gauge, which is much used across the world. So this same event now here is illustrated particle size distribution. This bin here, number 1, is 0.12 millimeters. So this is something the new sensor platform is able to see and able to detect particle by particle. So this is a number of particles seen, and these are the different size bins reported. When I mentioned that conventional present weather sensors can only see 0.5 millimeters and larger, it means that those conventional forward scatter sensors can only see these particles, and they miss all these. And then the optical distrometers, on their behalf, their limit goes somewhere around here, which means that all this amount of the water is unseen. The same event from a different perspective. We have here the accumulated liquid water, 0.05 millimeters, 0.2, 0.3 millimeters, very thin layers. At the onset of an event, the new sensor started seeing and reporting accumulated water, liquid water. 1 hour after that, the conventional forward scatter sensor started doing the same, with the same slope, with the same curve, while something like 2 hours later, the weighing rain gauge started reacting to the event. While these weighing rain gauges, they are actually quite good sensors when it comes to accuracy of higher amounts of water and accumulation and intensity, we wanted to show the same case, actually more cases and more statistical format against a weighing rain gauge. So here on the left hand side we have a liquid water accumulation comparison between the new sensor and weighing rain gauge, and we put 60 different rain events in the liquid water accumulation amount. So here is the weighing rain gauge, and here is the new forward scatter sensor. So they go very nicely in correlation on the slide. Why we have here more reports of the light cases for the FD71P is the fact that we can see beyond. So we have the sensitivity there, as I described. Then on the other hand, on the right hand side, when we are talking about high amounts, so liquid water accumulation 1 millimeter, 5, 7 millimeters, so over a few hours of time they go hand in hand. So FD71P and then reference weighing rain gauge, actually the difference is very small. So we've indicated here the reporting difference, and the scale is, here is 0 difference and here is 0.2 millimeter difference. So they go hand in hand when we have a relatively high amount of accumulation. So this is something, when I started in this position 4 years back, I did not believe. My background resides in developing these sensors, so I initially started 20 years back in Vaisala, and I was responsible for the electronics design and electronics engineering of FS11 and FS11P sensors. So when the scientist told me that, Tommy, we will be seeing every particle hovering, floating or then descending in the atmosphere, which can be considered as precipitation, I challenged, I say that you are talking probably about something like a prototype, a reference sensor which costs hundreds of thousands or something like that. Can you do that in volumes? It was very difficult to believe that this happens. Now they witnessed, and it really happens with the production units, and we can provide the high performance high quality directly from production and deliver calibrated FD70 series units within a few months. So as a summary, we state we have 100% detection. We detect everything. So after we detect it, then we try and analyze and check what is the type of the precipitation. It's superior, so we actually improve the identification performance across the board for hail, for ice pellets, for snow, for light drizzle, freezing rain, and all those 11 different types listed. We have distrometer features in the same package, so droplet size distribution with 40 pins beginning from 0.1 millimeter in diameter, and then extended visibility reporting range. I think we have some time for questions, but before that I already said that grazie, attenzione.